In this video, I introduce dense passage retrieval for open domain question answering. Given a query, a retriever is used as a similarity function to find a document from a corpus that is most relevant to the query, or find a similarity ranking of a document with the query. TF-IDF uses the occurrence of a query in a document as a relevance score, defined as here, where n is number of documents and the logarithm term is used to reduce the importance of the term that occurs in the most documents. However, the relevant documents in open domain question answering models may not contain the terms in query. Python Match 25 incorporates saturation into TF-IDF, in which the relevant score increases faster when TF is small, then slowly when TF gets larger, and saturates at the TF limit, defined as here, where K is a hyperparameter that controls the score growing speed with the TF increasing. Dense passage retrieval does not compare a query and passages in the original space, and instead compares them in the latent space through a network retriever. Given a m-text passages with a different length, DPR maps all the passages to a low-dimensional and continuous space, where DPR can find the relevance between a query and the top key passages. A dense encoder EP maps any text passage P to a d-dimensional real-valued vector and builds an index for all M passages. At the runtime, a different encoder EQ maps the input query Q to a d-dimensional vector and retrieves the key passages of which vectors are the closest to the query vector. The similarity between the query and the passage is defined as here, which is decomposable so that the representations of M passages can be pre-computed. During inference time, DPR applies a passage encoder EP to all the passages and indexes them using maximum inner product search algorithm. Given a query queue at runtime, DPR computes a VQ and retrieves the top key passages closest to VQ. Suppose that a query vector X and n document vectors Y. The best matching document with a query is found by MIPS, as shown here. MIPS requires a product of a query and all documents. MIPS is reduced to a nearest neighbor search problem by using a transformation H1 and G1. Phi is a maximum of yi, as shown here. Since the NNS is irrelevant to shifts and rotations, the transformation aligns all vectors with their principal components. Mu and matrix M with mu replicated along its columns are used to singular value decomposition. Here is shown. Where each column of matrix W defines a orthogonal unit length eigenvector, so that each Wi defines a hyperplane onto which each yi star minus mu is projected. Matrix W is a rotation matrix that aligns the vectors to their principal components. The second transformation is defined as here by using G2 and H2, which can be used for Euclidean search. After this transformation, the points are rotated so that their components are in decreasing order of variance. Next, the transformed document vector in Y tilde is indexed by using PCA tree data structure. The pseudocode of the model is shown here. For more information, please check with these references. Thank you.